The development of nuclear energy is often popularly linked to Albert Einstein and his famous equation, E=mc². This association, while not entirely misplaced, tends to oversimplify a far more complex and collaborative scientific achievement. In reality, nuclear energy would almost certainly have been discovered and developed even without Einstein's theoretical insight. More importantly, its realization depended not merely on equations, but on a convergence of experimental physics, engineering innovation, and, critically, advances in metallurgy and materials science. The true turning point in nuclear energy came not from theory, but from experiment. In 1938, Otto Hahn and Lise Meitner identified nuclear fission, demonstrating that uranium atoms could split into smaller nuclei while releasing a large amount of energy. This discovery did not rely on Einstein's equation for its execution. It was grounded in chemical experimentation and nuclear observation. While E=mc² provided a theoretical explanation for the energy released, the phenomenon itself could be and was observed directly. The next critical step was the transformation of this phenomenon into a controlled process. Enrico Fermi achieved this in 1942 with the first self-sustaining nuclear chain reaction. Fermi's work depended heavily on neutron physics, experimental design, and practical problem-solving. It required understanding how neutrons behave in different materials, how to slow them down, and how to maintain a stable reaction. These were empirical and engineering challenges, not purely theoretical ones. Equally essential was the development of isotope enrichment technologies. Natural uranium contains only a small fraction of the fissile isotope U-235, making it unsuitable for sustained reactions without processing. Techniques such as gas centrifugation and gaseous diffusion were developed to increase the concentration of this isotope. These processes were feats of industrial engineering and precision mechanics, requiring large-scale infrastructure and technological innovation. Again, while theory guided understanding, it did not by itself produce enriched fuel. However, perhaps the most underappreciated pillar of nuclear energy is metallurgy. The operation of a nuclear reactor imposes extreme demands on materials: high temperature, intense radiation, mechanical stress, and chemical corrosion. Scientists and engineers had to develop alloys capable of withstanding neutron bombardment without becoming brittle, fuel claddings that could contain radioactive material under pressure, and reactor vessels that could endure long-term thermal cycling. Without these advances, reactors would have been unsafe or simply non-functional. Metallurgy did not just support nuclear energy, it made it physically possible. In this broader context, Einstein's contribution appears as one piece of a much larger puzzle. His equation described the potential relationship between mass and energy, but it did not predict the practical pathway to harnessing that energy. Nuclear energy emerged from a sequence of discoveries and innovations that were largely independent in their execution. The experimental identification of fission, the engineering of controlled reactions, the industrialization of fuel enrichment, and the material science breakthroughs that enabled safe operation. Thus, it is reasonable to argue that nuclear energy would have been realized even in the absence of Einstein's work. The physical processes underlying fission were discoverable through experimentation, and the technological challenges were solved through engineering ingenuity and material science. More than equations, it was the ability to manipulate matter, down to its structural and atomic resilience, that ultimately brought nuclear energy from theory into reality.